Hello there. In this video, we're going to look at a problem that comes about in discrete event simulation where we're dealing with handling arrivals into a system in a way that is time to event, of saying at the current time, sample how much time until the next event. And an issue that comes up with this is it's possible to step over and skip parts of a time-dependent trajectory because of how it steps over it. Maybe I should get into the example right away here. So we've got a time-dependent distribution that's customized here, where if the time is strictly less than 55, return that you have to wait 10 units of time until the next arrival into the system. And then also you've got if time is strictly less than 58, return 0.1 for the amount of time, and then return 10. And the issue you can come up that you can run into here is not actually observing any examples with interarrivals of 0.1, because you end up stepping over it by going, there's a time that is less than 55 for which adding 10 to it entirely steps over 58, right? So the issue there is, let's say that the time is just shy of 55, adding 10 to that actually puts it up to just shy of 65, meaning that you have entirely stepped over this amount of time that was between 55 and 58. So if I have just a simple queuing system here, we have our time-dependent distribution for the arrivals, and we've got, it doesn't really matter too much what the service distributions are here. We're just saying service times of 0, meaning that the customers, patients, whatever, are served instantaneously. And then we've got that the number of servers is infinite, meaning really that not that we're actually simulating an infinite number of data structures for the servers, but just to say that quite freely the services are completed instantaneously, and even if there were simultaneous services, that is also allowed for any number of them. Okay, so we set up a simulation from that network. We simulate for, in this case, units of time from 0 to 101. We get all of our records, and then we're just grabbing the arrival dates. So if we take a look at the arrival dates, we can see that there's 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And that if we were expecting there to be something accounted for in these rates between 55 and 58 that are a much higher inter-arrival rate, these are entirely forgotten. They don't show up. That still we've only got once every 10. So Q has a way of solving this problem where I'm sure there's actually multiple ways of solving this problem, but their solution is, well, first of all, we'll maybe should have set a seed before. But instead of using this custom time-dependent probability distribution, we can use something that Q calls a PoissonIntervals. Now, if you're just trying to simulate a Poisson point process with a homogeneous rate, you can actually just set your arrival time distributions to be exponentials, because a counting process with exponentially distributed inter-arrival times just is what a Poisson is. This is a little bit different of saying, well, yes, it's supposed to be Poisson in terms of within an interval, but we're allowing and breaking up time into different rates for different endpoints of time, so different intervals. So we have endpoints 3 and 4, and max sample date 10. And we can sample from this distribution or put it even right into, and that's already an instance, and get that higher density of inter-arrival times that we were hoping for in some interval of time that we wanted. Hopefully that is useful to you. If you're finding that you have one of these intervals of time that are kind of a ghost, that they just keep not showing up. It could be because of this problem of trying to sample over thresholds of time, and hopefully this provides a useful fix for your use case. I'll see you in the next video, and have a great day.